Good. All right. Okay, so as I said earlier, we're going to see how to solve inequalities. And I think I said this earlier, but I'll say it now anyway. By definition, an inequality is what you get when you replace the equal sign in an equation with one of these symbols. Any one of them. So just like equations can be true or false, so can inequalities. And that's where solutions come into play. Solutions are the numbers that you can replace the variable x generally for us by, and that makes the inequality true. So again, this is just another terminology. You know, math does have a lot of vocabulary. Now, there's also compound inequalities. That's where you have one of these. I don't know why I wrote or more, because I can't see how you can have more than two inequalities unless there's something I'm just not thinking, overlooking that is. But these are what we call compound inequalities. But it's the same idea, essentially, in that you want all numbers that satisfy both inequalities at the same time. Same thing here with this and this. That's all. You know, so inequalities, like equations, can be true or false. And they can also have solutions. And they can also have solution sets. And this is what their solution sets are depending on the inequality. So you can see that these intervals are solution sets, meaning that every number in them is a solution for the corresponding inequality. So for instance, anything less than b, right? Anything that satisfies this inequality is in this interval. Anything strictly between a and b is in this interval. Anything that's greater than a and less than or equal to b is in here, and so on. We also saw equations can have no solutions. I mean, you can have an equation such as 0 equals 1, right? That's never true. There's no solutions. So that solution is, the solution set is empty. Same thing with inequalities. You can have an inequality that has no solutions. The solution set, again, set is a fancy word for collection, you know, or group of, I guess. Then we have the empty set. That's just, again, the set that has nothing in it. There are two different ways of denoting it. I know this one's kind of different looking. It's a 0 with a dash through it. I think 0. I'm not sure who came up with this either, but it's just notation that mathematicians use. But they both denote the empty set. All right, so we have that. Okay, now remember how when we solved equations, we couldn't do anything we wanted to, right? We were restricted to certain manipulations. Manipulations we could do preserved the solution set. In other words, there were only certain manipulations we can do, right, when solving an equation. You know, we didn't want to remove any solutions or add any solutions to the original solution set, to the original equation, to the solution set for the original equation. There were certain manipulations we could do. You know, like we could add the same thing to both sides. We can multiply or divide by the same non-zero number. Well, it's the same thing with inequalities. Namely, there's only certain manipulations we can do to solve an inequality. I mean, what I'm crossing out is technically true. It's not going to be an issue for us. But there's only certain things we can do. And basically, you can simplify either side. You can add or subtract the same expression to both sides. With multiplication division, you have to be careful though. I mean, you could multiply or divide both sides by the same non-zero number or expression, but if you multiply or divide by something negative, then you have to do something extra. You have to turn the inequality around or flip it. Now, what do I mean by that? What I mean, let me see if I could draw it, because I don't have it here. When I say turn it around, the inequality around, less than would turn into this. Same thing with the non-strict inequality. So this would turn, would turn into this. Okay. And of course, you would have the other way. That is, you can have this turn here. And finally, boy, this is a lot of drawing. Hope this is helping, but I think it is. So it's really what it sounds like when I say turn the inequality around. Oh boy. Let me just erase that part. Drew the wrong thing. Let me just get that. Oh, wrong one. Basically, what I mean is you how do I say this? You turn the inequality 180 degrees, you rotate it, you flip it, you invert it, if that makes sense. That's what you have to do when you multiply or divide by something negative. Okay? See, you turn it around, so it's facing the opposite direction. Kind of like with an arrow on. Okay? Now you might be thinking, well, wait a minute, why would you have to do that? Well, I'm going to show you. We have this inequality, let's say, right? 1 is less than 2. You know, and we know that's a true statement. 1 is less than 2. That is true. But let's say we multiplied both sides by -1, and we forgot to turn this around for whatever reason. Well, then we're saying -1 is less than -2. Well, as far as I know, that's false. -1 is bigger than -2. So if we do not flip the inequality around, so if we do not turn, let's say, less than to greater than, right, as on the previous slide, less than greater than, so the inequality would flip. So let me see if I could draw it. Right, this would actually become this if we turn it around. Right, if we don't turn the inequality around, you know, something that was true becomes false. And really, to bring in variables, here's an example. If you look at the one down here, this one, here, let me get the laser. This one, right, is false for no matter what x is. Okay, no matter what number you plug in for x, this is going to be a false statement. But if I multiply by -1 on both sides, and I forgot to turn the inequality around, well, what happens? It's not false anymore. In fact, it's actually always true. In other words, it should be like this. So if I forget to turn it around, then false becomes true and true becomes false. So you have to remember to flip the inequality. That's what I'm saying. Okay. All right. Good. Okay, that was fun. Well, let's do an example. Let's suppose we want to solve this inequality. Now, okay, now again, simplifying each side is something we can do, but you can really see though that, you know, you can't simplify either side. You can't simplify any further. So let's solve this. Now, what you want to do, it's kind of like with equations, you want to make sure you get x, the variable, all alone on one side, generally the left side. And that's what I do here. You want to get x all alone, right? So this is the top line. So you don't have to go in this order necessarily, but what I did was I subtracted 1 from both sides, right? This 1 gets killed off. This -3 becomes -4. Then, again, I want x to be all alone, so I subtract 7x from both sides. So I get -2x is less than -4, which is written this way. But notice, though, I want x all alone, so I divide by -2. And by dividing by -2, I flip the inequality around. See? So you have to remember to turn the inequality around. So in this case, this inequality is equivalent, that is, it has the same solution set as this one. And this one we know how to solve easily. It's just all numbers greater than 2. Graphing it, it looks like this. Notice also that we're not including 2, so I have an open circle above it. And again, we have the arrow going to the right because we want everything bigger than 2. And we saw that the only symbol that would work is this symbol. You can't put a number here because you're going to miss solutions. Okay, that's one example.